Welcome back to the video course on fluid mechanics. In this lecture today we will discuss one of the important topic on laminar and turbulent flow. So, the main objectives what we are studying in this chapter. So, here we will be checking how the forces due to momentum changes on fluids and the viscous forces how it compares. So, the effect of viscosity will be how the flow parameters will be changing, how what are the changes takes place, how the fluid will be behaving with respect to the viscosity. So, how the system will be either laminar or turbulent. So, that we will be checking, and then we will be looking into say various types of flow. So, we will be checking one of the important aspect of so called Reynolds experiments, where say Osborne Reynolds he utilized say his experiments to classify the flow as laminar, turbulent and other say the various cases, and then we will be discussing the laminar flow between parallel plates. We will be discussing laminar flow in pipes, and also we will be discussing the turbulent flow in pipes. So, these are the main objectives which we will be studying or which we will be discussing with respect to this particular chapter on laminar and turbulent flow. So, now if you see the nature, you can see that the flow can be most of the time either it can be laminar in nature or it can be a turbulent in nature. So, here you can see in this slide, say if you consider say river, you can see that some parts of the river is, you can see the flow is quite calm and it is very slow, flowing in a very slow pace, and you can see that the flow is which is say it is in laminar type or it is in flow is in layers, and but you can see some parts where we can see say where this some gates are there with respect to this bridge here, and then you can see that some disturbance are created, and then you can see that the laminar type of flow in this river is transformed to turbulent flow. Or you can see whenever a boat is moving just like here, then you can see just behind the boat the flow is totally turbulent or totally disturbed, and then you can see that means here the same in a river at some parts say the flow may be laminar and some parts the flow may be turbulent. So, and similarly this is the case as far as open channel is concerned or river is concerned, but you can see say in pipe flow also. So, in this photograph you can see that so whenever we open the pipe very slowly, when the valve is opened very slowly, you can see that flow will be coming just like in layer type or laminar type, and when you are opening more, when the discharge is more, when the velocity is more, you can see that the lot of disturbance, lot of mixing takes place and the flow become turbulent. So, this again we will see how the flow can be laminar or turbulent in an experiment which we conducted in our hydraulics lab. So, here you can see say one of the experiment which we did in our hydraulics lab, where say a sump pump test is done. Here you can see one open channel, so which is coming that flow is initially laminar, and then here there are some pumps, and then with respect to due to the pumping effect the flow velocity or the discharge variation takes place and the velocity is increasing, then you can see that the laminar flow at some part of the channel becomes turbulent. So, you can see that here the flow becomes very much say disturbed, and then the laminar flow is transformed into turbulent flow. So, like this you can see many places wherever say initially the flow may be laminar, and then sometimes it may be laminar, sometimes it may be turbulent. So, with respect to this, now we will be discussing further say what are the important parameters which say decide whether the flow is laminar or whether the flow is turbulent, and how we can classify whether the flow is laminar, turbulent, and then we will be discussing further theories related to the laminar and turbulent flow. So, now the same experiment which you have seen the video show, you can see here this is a laminar flow, and here due to the pumping effect it is again becoming turbulent. So, here some places it is laminar, some places it is transitional stage, and here you can see the flow becomes turbulent. So, now say with respect to the various theories on laminar and turbulent flow, you can see that say most of the times we are dealing with real fluids. So, real fluids are concerned, there is of course viscosity of the fluid is very important parameter, and then viscous effects play a major role. So, you can see that due to the viscous effect as shown in this slide here, say you can see due to the viscous effect there will be no slip condition on the boundaries, and then say you can see there will be say the flow is say here before becoming fully developed due to the boundary layer effects and the viscosity effects. Say the some parts say initially the flow can be laminar, and then it can be say after sometimes due to depending upon the flow condition it can become turbulent. So viscous effect is very important in fluid mechanics in the case of real fluids. So with respect to this we can see that say due to the viscosity or the viscous effects the fluid tends to stick to the solid surface. So in the previous slide you can see here due to the viscous effects or viscosity the fluid is tending to stick to the solid surface here these both sides, and then say due to this sticking effect or no slip condition boundary layer is created, and then say the flow pattern can change whenever flowing fluid is interacting with a solid surface. So similarly we can see say the stresses also important say plays major role as far as the flow is concerned, whether say desired when we are say classifying the flow into laminar or turbulent. These stresses are also very important, say shear stresses, normal stresses, and various say within the fluid how it will play, that is also very important. So while discussing this laminar and turbulent flow, another important aspect is the Newton's law of viscosity. So we have already seen in our introductory lectures that say Newton's law of viscosity states that the shear stress is proportional to the velocity gradient. So tau is proportional to du by dy. So that with respect to the viscosity or with respect to the dynamic coefficient of viscosity, we can write tau is equal to mu du by dy. So this is the Newton law of viscosity. So the shear stress is equal to dynamic coefficient of viscosity multiplied by the velocity gradient. So this Newton law of viscosity is also very important as far as say when we discuss the laminar and turbulent flow. And then say now we are discussing the laminar and turbulent flow. So with respect to this it will be interesting to see the earlier classification which we have studied, which we have discussed in the introductory lectures, say the types of fluid flow. So when we discussed earlier lectures, we have seen that say the fluid flow can be classified with respect to the rheological consideration like liquids and gases, and then dilational consideration like it is compressible or incompressible, then temporal variations with respect to time, how the fluid, whether it is a transient or steady state, and spatial dimensions, whether one dimensions, two dimensions, whether the flow which we are considering is one dimension, two dimensions or three dimensions, and also the motion characteristics we have seen that whether say with respect to say now as we have seen whether it is laminar or turbulent. So these types of fluid flow we have already discussed earlier. So here with respect to when we are going to discuss in detail about the laminar and fluid turbulent flow, say the various aspects, whether what kind of fluid we are dealing, what kind of say the motion characteristics, or whether the spatial dimensions which we are considering, or whether the temporal variations, all these are very important when we discuss whether the fluid is laminar or turbulent. So accordingly this chart we have seen earlier in our introductory lecture, say we have seen that the fluid flow can be classified as whether gas or liquid, or then with respect to the dilational characteristics whether the fluid flow is compressible or incompressible, or whether with respect to temporal variations whether it is transient or steady state, and with respect to the viscous effect whether it is viscosity is considered or inviscid or non-viscous fluid which we are considering, and then also rotational flow or irrotation flow, especially turbulent flow, the rotational effect is very important, and then also this dimensions which we consider whether one dimension, two dimensions or three dimensions. So these types of fluid flow with respect to what we are discussing now, laminar or turbulent flow, it is many of these parameters are very important. So now Also, with respect to the, say, before going to the more details of laminar and turbulent flow, the types of fluid flow also can be we can classify according to the geometry of flow field. So, say most of the flow with respect to the geometry, we can classify whether the fluid does the internal flow or external flow. So, here now say internal flow means, say, it involves flow in a bounded region. So, just like in a pipe flow. So, here you can see there is a pipe flow here. So, here this is a pipe flow. So, now the flow is taking place in this way. So, now you can see here the internal flow, we are saying now the flow in the pipe is internal flow. The reason is, so here you can see that the flow is confined within this boundary of the pipe. So, that is why we say that it is internal flow. So, the approach which we will be say analyzing this kinds of flow will be different, just what we are discussing, so called external flow. This is the pipe flow is an example of the internal flow. And now other classification based upon the geometry is the external flow. So, here the fluid flow in an unbounded region. So, we are considering the fluid flow in an unbounded region. So, it can be just like in a flow pattern around a body immersed in the fluid. Say for example, when there is a say a building is concerned. So, if this is a building which we consider, so with respect to this, say if the wind comes, so you can see that what happens with respect to, say, surrounding the building. So, this is, say, very important for many engineering design. So, this kinds of flow where the flow, say what happens with respect to the surrounding of a particular body or particular structure, or say this kinds of flow where the fluid flow is in an unbounded region. So, that is so called external flow. So, this is also very important when we discuss the laminar and turbulent flow. Also, the real fluid motion is significantly influenced by the boundary. So, say either it can be an internal flow or it can be an external flow. Say as in the case of a pipe flow, you can see that whenever, say, the boundary, so the solid surface where the fluid is have a no slip condition. So, the boundary is very important. So, the no slip condition and the boundary layer formation is very important as far as flow is concerned, whether it is internal flow or the external flow where surrounding a building or whenever a boat is moving in a river. So, we can say that with respect to that, say, surrounding the boat or surrounding the ship, what is happening, that is very important. So, the formation of the boundary layer is also very important. So, with respect to this laminar and turbulent flow which we will be discussing today, so all this, say, whether what we are discussing, whether it is external flow or it is internal flow, that is also very important. So, now say as far as internal flow which we discussed is concerned, so you can see that here say a pipe flow. So, the fluid, say we will say that say the boundary effects likely to extend throughout the entire flow, as you can see here in this slide. So, we say here this it is a fully developed say a velocity profile is formed here, and then so this is say the now after some time the boundary effects say is still there, but still it has overcome, and then the boundary effects likely to extend through the entire flow. So, this is say again the internal flow, and then as far as external flow is concerned, you can see that the frictional effects are confined to the boundary layer next to the body, and then there here the drag or lift are more important. So, here say when we discussed, say whenever say for example whenever a balloon is just say lifting through the air, then you can see that what is, say, with respect to the lift effect or the drag effects what happens. So, that is also very important as far as the types of fluid flow is concerned. So, this is the case of an external flow. So, as far as the laminar and turbulent flow is concerned, so we have to see that whenever we discuss these kinds of problems, we have to see whether the flow is external flow or internal flow. So, now say for the pipe of free flowing water, say if we inject a dye into the middle of a stream. So, here you can see just say if we inject say for example a dye to the middle of a pipe flow. So, you can see that say with respect to the velocity of the flow in the pipe. So, initially you can see that the pipe flow velocity, the fluid velocity is small, then you can see that the dye which we are injecting, it will be just moving just as like a filament of dye. So, just in layers. So, this is we can say now it is laminar flow, where the flow is in layers, and then there is no disturbance takes place. But then we can see that the velocity of the flow increases. So, then you can see that after some time here, the second figure here, you can see that say there is slight disturbance starts. Earlier the flow was in layers, and then slight disturbance starts, and finally you can see that say when the velocity is further increased, you can see that the dye is totally mixing within the fluid, and then say the lot of disturbance you can see, the fluids are intermixing, and then you can see there will be dye will be totally mixing with the fluid inside the pipe. So, here you can see say initially when the velocity is small, and then we are injecting only a small piece say mass of say filament of dye, you can see it is laminar, and then when the velocity is increased, then you can see it becomes a transitional flow, and then finally lot of mixing takes place, and then you can see that it becomes turbulent flow. So, the same in a similar say way we can see say for the flow may be for some time it can be laminar. So, but if the flow parameters like velocity changes, then it becomes transitional, and then further we can see that it become turbulent. So, this is the way the say depending upon various flow parameters, the fluid flow changes from laminar to turbulent. So, now with respect to this what we discussed, we can say what is a laminar flow. So, in the laminar flow you can see that the fluid moves in layers of laminas. So, we can define the laminar flow as the fluid moves in layers of laminas, one layer gliding smoothly over and adjacent with only molecule interchange of momentum. So, you can see here with respect to this figure in the first figure. So, you can see the fluid is moves in layers of laminas, say one layer is gliding over smoothly over and adjacent with only molecule interchange of momentum takes place. So, this is the definition of a laminar flow. But then you can see that, as I mentioned, when the velocity or other flow parameters changes, then small kinds of mixing takes place. Instead of smooth gliding, you can see that there is mixing starts, and then we can say that the flow is transitional. And then as far as turbulent flow is concerned, you can see here say there is erratic motion of fluid particles with a violent transverse interchange of momentum. So, the turbulent flow we can define as erratic motion of fluid particles with a violent transverse interchange of momentum. So, here you can see whenever we injected the dye, when the velocity is increased or other flow parameters change, then you can see that there is total mixing of the dye takes place within the fluid, and then the flow become totally turbulent. So, we can define the turbulent flow as wherever the flow there is erratic motion of fluid particles with a violent transverse interchange of momentum. So, now to say the question here is say whenever a flow is say if a flow is there, a fluid flow, how we can define whether it is at laminar stage or whether it is a transitional stage or whether it is in turbulent stage. So, this is a very important question, since say most of the time we will be dealing with the pipe flow or we will be dealing with open channel flow or river flow or canal flow, many kinds of flow. So, it is very important to see that whether the fluid flow is laminar or whether the fluid flow is a transition state or it is turbulent. The reason is that most of the theories whatever we are applying to laminar flow may not be applicable to turbulent flow. So, many flow parameters to be changed, the theory will be changing as far as when the flow is changing from laminar to turbulent. So, in all the cases it is most of the fluid flow cases it is very important to define whether the existing flow is, whether it is in laminar state or whether it is just in the transition state or it is turbulent state. So, this say a large number of scientists and engineers worked on this topic, and then say in early in the 19th century, say 1880s, one famous scientist Osborne Reynolds defined a number called Reynolds number. So, nowadays say after this Reynolds introduced this dimensionless number called Reynolds number, so with respect to this Reynolds number we can define whether the concerned flow is laminar or turbulent. So, this Reynolds number say which is used to define whether the flow is laminar or turbulent. So, it shows the nature of flow. So, whether the flow is laminar or turbulent, and then it says relative position along a scale. So, with respect to the dimensionless number or so called Reynolds number defined by Osborne Reynolds, we can put a scale whether with respect to this scale, say if the Reynolds number is say 500 or 1000 or 2000, and then it is laminar, say as in the case of pipe flow, or when it exceeds 4000 it become turbulent, and then say for example in open channel flow, if it is less than or equal to 500, whether it is laminar, or when it exceeds 600 or 1000 it become turbulent. So, this Reynolds number is a scale say relative, which gives a relative position whether the flow is laminar or turbulent. So, now Osborne Reynolds defined this Reynolds number based upon a large number of experiments with respect to fluid movement. He conducted experiments called Reynolds experiment, and he conducted this experiment in 1880s, end of 19th century, and then he defined this so called Reynolds number. So, now this Reynolds experiment we can see here what Osborne Reynolds did is, say here there is a small tank where water is filled, and then a pipe is connected with respect to that tank, and then there is a valve is attached at the end of the pipe, and then he introduced a small tank inside this large tank where some dye has been put, and then say through a small nozzle he introduced the dye to the pipe where the pipe starts, like in this figure, and then what he did say with respect to say the valve opening. So, he started say slowly he started to open this valve, and then you can see here as shown here, say the fluid say will be, the flow will be from what is with respect to the dye, and then the fluid movement here you can see that the fluid movement is now with respect to dye, we can see it is laminar in nature. So, here with respect to what we have seen here, say with respect to this color, it is easily we can identify. So, it is initially whenever the valve opening is small, the velocity is small, and the discharge is also small, and then you can see and the flow is say with respect to dye, we can visualize the fluid is moving in layers or in laminas, and then when the valve is opened more, we can see that this the fluid which is moving in laminas or in layers, then some disturbances starts, and then you can see that there is some oscillation starts for the fluid, and when again further when the valve is opened, you can see that further say when the valve is opened more, the velocity increases, and then with respect to the dye movement, we can visualize that there is mixing takes place, interchange of masses takes place, and then there is erratic motions takes place, and finally as we have seen here, the flow become turbulent. So, that is what say Osborne Reynolds did say in 1880s, and then with respect to a large number of experiments as mentioned here, so he defined so called Reynolds number, which we have seen. So, after many experiments, Reynolds showed that say a particular ratio, so rho Vd by mu, where rho is the mass density of the fluid, V is the average velocity, D is the diameter of the pipe, and mu is the dynamic coefficient of viscosity. So, this ratio rho Vd by mu helps to predict the change in flow type. So, he defined this number as Reynolds number. So, this number is a dimensionless number. So, Osborne Reynolds defined this number as Reynolds number, and actually this number is the ratio of inertial forces to viscous forces. So, he puts this number Reynolds number is equal to inertial forces divided by viscous force, and for pipe flow we can define as rho Vd by mu, where rho is the mass density of the fluid and V is the average velocity, D is the diameter of the pipe, and mu is the coefficient of dynamic viscosity. So, similar way we can define this Reynolds number for open channel also. So, with respect to his experiments, he put this Reynolds number as a scale to define whether the concerned fluid flow is laminar or whether the concerned fluid flow is, whether it is in the case of transitional stage or whether it is in the case of turbulent stage. So, now with respect to this Reynolds number, we can say, for example, if we consider pipe flow. So, as I mentioned, say whether the flow can be pipe flow or open channel flow, river flow, like that. Say if we consider for pipe flow, we can show that, say generally with respect to various conditions, we can say that when the Reynolds number is less than or equal to 2000, say in this range of 2000 or less than 2000, we can see that the flow is laminar, and then say a range of between 2000 to 4000, we can see that the mixing starts, and then disturbance starts, and then transitional state occurs for pipe flow, and then say beyond 4000, when the Reynolds number is greater than 4000, we can see that the flow become turbulent. So, with respect to for pipe flow, with respect to Reynolds number, we can say whenever the Reynolds number is less than 2000, say we can say the flow is laminar, and between 2000 to 4000 we can say the flow is say at a transitional stage, and then beyond 4000 the flow is turbulent. So, in experiments, through experiments we can show when the flow is laminar. With respect to the Reynolds number also, we can see that whenever the flow is laminar, the velocity will be low. So, it will be low velocity, and at transitional flow we can see that there will be medium velocity, and when the flow become turbulent, the velocity is high or high velocity flow. So, this is the case of pipe flow, and similar way if you consider, say if you do experiments in open channel with respect to say various conditions, generally we can say that the flow will be laminar when the Reynolds number is less than or equal to 500, and then say from 500 to 2000 it may be at a transitional stage, but this can vary slightly, and also beyond 2000 you can see for open channel flow it can be turbulent in nature. So, this exact range depends on various other flow conditions exist in the flow regime. So, various other conditions, say boundary conditions or the initial conditions, depending upon these kinds of various conditions, this range can vary, but approximately this is the range put forward by various scientists and engineers for open channel flow and pipe flow. So, now with respect to the Reynolds experiments which we have seen, say we can put forward certain interpretations. So, first one is say when viscous forces are dominant. So, we have seen that see the Reynolds number is the ratio of inertial force to viscous force. So, with respect to this we can say we can interpret when the viscous forces are dominant. So, that there is the flow is slow or the Reynolds number is low, and then they are sufficient enough to keep all fluid particles in line or flow is laminar. So, even though if there is any tendency for any disturbances, then due to the here for this particular kind of flow, wherever the velocity is small or the slow flow and low Reynolds number, we can see that the disturbance will be dampened, and then here the viscous force are dominant and flow is laminar. And then the say whenever the fluid flow is faster or the velocity is larger, the Reynolds number is larger, and then we can see that inertial forces dominate over viscous forces, and then finally the flow is becoming turbulent. So, this is what is happening. So, whether the with respect to the fluid flow velocity, we can see that say when the Reynolds number is lower or higher, and then say whether the viscous forces are dominant or the inertial forces are dominant. So, accordingly we can say that we can classify whether the concerned flow which we are dealing is laminar in nature or turbulent in nature. So, now also while conducting these experiments, we can say, even though we have seen that say certain range the flow is laminar, and beyond that it become transitional or turbulent. So, say when we conduct large number of experiments, we can see that we can define a lower critical Reynolds number, where the Reynolds number above which the flow changes from laminar to transitional or turbulent. So, this is so called lower critical Reynolds number, and then we can define say when we further say, for example, the velocity of flow with respect to the valve movement, if the velocity is reduced. So, in a similar way, when the flow is transforming from laminar to turbulent, so in the opposite direction, when we reduce the valve opening, then you can see that the flow velocity will be slowly coming down, and then there will be a transition takes place from turbulent to transitional or turbulent to laminar. So, there we can define a Reynolds number called upper critical Reynolds number. So, here the Reynolds number below which turbulent flow changes to laminar flow. So, this critical Reynolds number, we can have two ranges, one is lower critical Reynolds number and other one is the upper critical Reynolds number. So, this critical Reynolds number which we have seen, this critical Reynolds number based upon which we classify the flow as laminar or turbulent. So, this varies depends upon various flow conditions like what kind of fluid, then what are the boundaries, just as we have seen, whether it is pipe flow or whether it is open channel. So, it is difficult to put an exact range, say when exactly the flow is transforming from laminar to turbulent. So, but this depends upon various other different flow conditions also. But generally we prescribe a lower critical Reynolds number, where the flow changes from laminar to turbulent or transitional, and then upper critical Reynolds number, where the turbulent flow changes to laminar flow. So, now say also you can see whenever we conduct these kinds of experiments in the laboratory, we can see that say this laminar flow, which is, say we have seen it is flowing in layers, and then say some stages we can see instability of laminar flow. So, here the inertial forces associated with the fluid mass try to amplify the disturbances in the flow. So, whenever say initially if the flow is laminar, but then there can be different kinds of disturbances like boundary friction or the shearing effect or other kinds of effects, then you can see that the inertial forces, say with respect to the fluid which is flowing, inertial forces associated with the fluid mass try to amplify the disturbance in the flow. So, then we say that there is instability of laminar flow. So, then viscous forces try to damp these disturbances, but the various forces which is again trying to amplify the disturbance, if it is predominating above the viscous forces, then you can see that the laminar flow, we say that the laminar flow become unstable, or instability of laminar flow takes place, and depending on the flow, fluid characteristics like mass density, viscosity, velocity gradient, proximity to boundary, etc., the disturbance are dampened or amplified. So, the disturbance for the given conditions, if the disturbance are dampened, again the flow will be continuing as laminar. So, it will be continuing as laminar flow, but if the disturbance are amplified further due to various forces like shear force or various frictional forces, then it may change from laminar to turbulent flow, or we say that the laminar flow become unstable or instability of laminar flow takes place. So, this if the disturbance are dampened, the flow is laminar, otherwise we say that the flow becomes turbulent. And also say now, say with respect to what we have discussed, so we can see that as far as turbulent flow is concerned, the various important characteristics which we can observe in nature or observe in the laboratory includes say irregularity. That means here you can see with respect to the, say here, say when flow become turbulent, you can see that when the flow is laminar, you can see it is very regular in say the one layer is sliding over the other one, it is very much regular, but you can see for when the flow become turbulent, some of the important flow characteristics of turbulent flow are, first one is irregular in nature, the flow is irregular, and then second one is diffusivity. As far as diffusivity is concerned, you can see in the case of laminar flow, we say that the molecular diffusivity is more important, but as far as turbulent flow is concerned, the turbulent diffusivity is much more than the molecular diffusivity, and then the flow is changing from laminar to turbulent. And then some of the other important characteristics are high Reynolds number, as we have already seen, and then many cases you can see that the flow may be rotational nature. So most of the laminar flow it can be say the rotational effect will be very minimal, or it can be even irrotational in nature, but most of the turbulent flow you can see that all the turbulent flow the motion will be rotational nature. And due to this, we have to, most of the time we have to consider the fluid flow in 3 dimensions, since one dimension or 2 dimension, it will be very difficult to see what is realistically happening, how the disturbance takes place, which way the disturbance, which direction it takes place. So most of the time, as far as turbulent flow is concerned, we have to do 3-dimensional analysis. So motion, as far as turbulent flow is concerned, motion can be rotational and 3 dimensions, and then the fluctuations you can see here, the fluctuations can be wide spectrum. So if you just consider, say for example, say if the flow is laminar here, so the flow is laminar here, but as far as turbulent flow is concerned, you can see that whenever the flow becomes turbulent, the fluctuations takes place will be say wide spectrum. In wide spectrum the fluctuations takes place. And then also another important flow characteristic of turbulent flow is motion is dissipative. So various energies like heat energy, all this will be dissipated with respect to the turbulent flow. So with respect to the discussion so far, we can say that the turbulence in a flow it is a feature of flow, but it is not as a fluid property. It is very difficult to say that a turbulent it is not a fluid property, but we can define it as the turbulence is a feature of the flow. So whenever a flow is we have to see that if we say it is turbulent flow, it is the feature of the flow, but it is not a fluid property. So now further we will be discussing various aspects of the laminar flow and turbulent flow in detail in this chapter. So initially we will be discussing the laminar flow, and then we will be discussing the turbulent flow. So now we will discuss laminar flow in detail. So initially we will see the various flow characteristics as far as laminar flow between parallel plates, and then we will be discussing the laminar flow in pipes. Then further we will be discussing the turbulent flow. So now first one is laminar incompressible flow between parallel plates. So here we will be deriving various relationships like the velocity variation, and then the shear stress variation, etc., as far as laminar incompressible flow between parallel plates. So first let us consider the flow of a viscous fluid between 2 very large parallel flat plates spaced at a distance of 2h or equal to 2y apart. So we consider here the laminar flow. So the laminar flow, what we are considering here is, say we are considering 2 very large parallel plates like this. So now if you consider this sheet of paper as a parallel plate, so what we are doing here is, say in between, say 2 parallel plates are placed like this, and then say 2 parallel flat plates. So in between, if a fluid flow is there, so laminar flow, how the flow parameters varies, so that we are going to discuss here the laminar incompressible flow between parallel plates. So here we assume since it is parallel flow, we assume the flow is to only one velocity component we will be considering, and then we also assume the flow is to be steady state and the fluid is incompressible. So this kinds of flow, wherever the flow between 2 large parallel plates, this kinds of flow is generally called plain Poisson flow. So the flow between 2 infinite parallel plates, which is laminar in nature, at the parallel plates are placed at a distance, So this kinds of flow between these parallel plates is known as plain Poisson flow. So now we will discuss in detail various flow parameters, various how the velocity variation takes place. So here we can see the velocity profile for flow between parallel plates. So one parallel plate is here and another one is just placed 2h above at a distance 2h. So here the flow is between these parallel plates. So if you plot the velocity profile, you can see that now we are discussing the real fluid. So due to the viscosity of the fluid, you can see there will be no slip condition. So that here the velocity on this side, it will be on the upper plate where the contact between fluid takes place, the velocity will be 0, here the velocity will be 0, and then you can see that due to the, since the fluid is between two parallel plates, so generally the velocity will be maximum at the center, and then you can see if you plot the velocity, then you can see it will be parabolic in nature. So starting with 0 on both sides, and then it will be maximum at the center. So if you plot the velocity, we can see that it will be parabolic in nature, 0 on the both sides of the parallel plates, and then maximum at the center. So now we will be discussing further we want to get the velocity variation, we want to find out how the velocity variation, and once the velocity variation is known, we can find out the shear stress or other fluid flow parameters. So now we are considering the flow which we considered is, say we can say it is 2-dimensional nature. So now for 2-dimensional flow, we have already seen that the continuity equation we can write del u by del x. So the velocity in x direction is u, velocity in y direction is v, then we can write from the continuity equation as del u by del x plus del v by del y is equal to 0. So this is the continuity equation, and now we can see that since the streamlines curve straight, so here the stream is, if you plot the streamlines are parallel, so that we can say that and it is parallel to the x direction. So you can see that here the velocity component v is equal to 0. So finally what say we can see for this particular case, there will be only one velocity component in x direction, the other velocity component v is equal to 0. So from this continuity equation we can write del v by del x is equal to del v by del y, since v is equal to 0, that del v by del x is equal to del v by del y is equal to 0. So if you use this, put in this continuity equation, we can write del u by del x is equal to 0. So that means for this particular case, laminar incompressible flow between parallel plates, velocity does not change with x, velocity field v is equal to 0, and the velocity u is changing with respect to y only. As you can see the plot here, you can see the velocity is varying with respect to y only. So u is a function of y as written here. So now finally, say with respect to the simplifications, we can see that the flow is one-dimensional and unidirectional or one-directional. So the flow is one-dimensional flow and then one direction. So this type of flow with the velocity profile unchanging as the fluid moves downstream is so called fully developed flow. So this kinds of flow, this type of flow with the velocity profile unchanging, you can see the velocity profile here, it is unchanging with respect to the as the fluid moves downstream. So we say it is fully developed flow, and now we want to find out. So we have already seen the velocity variation here, and now we want to find out the velocity distribution. We want to get an expression for the velocity variations so that we can plot the velocity. So here we derive the expression for velocity by using the first principle or the Newton's second law we can apply here. So we have already discussed about Newton's second law and its application earlier. So by using Newton's second law for a particle, if you can say particle in the control volume which we are dealing, so we can say write the mass of particle multiplied by the acceleration of particle is equal to net pressure force on the particle plus net gravity force on particle plus net stress force on particle. So you can see from the Newton's second law for a particle which we consider the control volume, we can write mass of the particle multiplied by the acceleration of particle, that is equal to net pressure force on particle plus net gravity force on particle plus net stress force on the particle. So here we use Newton second law to derive the equation. So, for the x directions from the Newton's second law we can write, so mass into acceleration is equal to pressure force plus gravity force plus shear force. So, for if we consider a small fluid element for which the mass is delta mp and its acceleration is ax in x direction, so that is equal to delta fx pressure plus delta fx gravity plus delta fx shear. So, now here if you consider the delta fx is concerned, so here we can write down the expression for this by using here, and we will consider a control volume, that means here the fluid flow between parallel plates is here. So, we consider a small fluid element and then we can write the pressure force, say we will write with respect to this fluid element on the left side we can write P minus del P by del x into delta x by 2. If delta x is the size of the fluid in x direction, delta y is the size of the fluid in y direction, and the plate is placed at a distance of 2y. So, here the pressure force is P minus del P by del x into delta x by 2, and other side of the fluid element P plus del P by del x into delta x by 2, and then other, say this side is concerned we can write P plus del P by del y into delta y by 2, and the opposite side it will be P minus del P by del y into delta y by 2. And similarly the shear stress is concerned, which is another important force, shear force. So, we can write on this side tau plus del tau by del y into delta y by 2, and on this side it will be tau plus del tau by del x into delta x by 2, and this side of the fluid element it will be tau minus del tau by del y into delta y by 2, and this side it will be tau minus del tau by del x into delta x by 2. So, now we are considering this control volume and we are considering a fluid element. So, all the pressure force and shear force is concerned. So, finally we can write with respect to this the delta fx pressure we can write del p by del x into delta x into delta y into, if we consider the unit thickness it is multiplied by 1. So, similarly we can write the gravity force is concerned, delta fx which is acting on the fluid element will be rho gx into delta x into delta y into 1. So, this gives the gravity force. So, and the shear force is concerned we can write with respect to the earlier figure shown, we can write del tau by del y into delta x into delta y into unit thickness. So, now by using Newton's second law we have written for the fluid particle or the fluid element is concerned, the mass of the fluid element or fluid particle multiplied by its acceleration, that is equal to the pressure force on the fluid particle plus gravity force on the fluid particle plus shear force on the fluid particle. So, we have derived, we got the expression for the pressure force on the fluid element as the minus del P by del x in delta x in delta y, and the gravity force we got rho gx in delta x in delta y, and shear force we got del tau by del y into delta x into delta y. So, now the acceleration of the particle, as we have already seen earlier, we can write ax is equal to del u by del t plus du u into del u by del x plus v into del u by del y. So, this gives say the local acceleration plus convective acceleration. So, ax is equal to del u by del t plus u into del u by del x plus v into del u by del y. So, you can see here we are considering the flow as steady state. So, this is 0 and del u by del x is 0 and then v is 0. So, finally, ax is equal to 0. So, finally, the Newton's law reduces to only the force is equal to the pressure force plus gravity force plus shear force on the fluid is equal to 0. So, finally, we get the equation as minus del p by del x plus rho gx plus del tau by del y is equal to 0. So, this is the expression which we get for the fluid element which we consider. So, now in the earlier equation if you introduce so here this rho gx is concerned. So, introducing z coordinate pointing upward opposite the gravity vector we can write minus del p by del x minus rho g del z by del x plus del tau by del y is equal to 0. And here you can see that the pressure P and the acceleration due to gravity G are constant. So, that we can combine these two terms and write del by del x of P plus gamma Z plus del tau by del y is equal to 0. So, we can finally get the expression as del by minus del by del x of p plus gamma z plus del tau by del y is equal to 0. So, similar way this what we have seen the earlier equation is in the x direction. So, similar way we can write in the y direction minus del by del y of p plus gamma z plus del tau by del x is equal to 0. And now here you can see since the velocity profile do not change in x direction, we can write del tau by del x is equal to 0, and hence we can write del by del y of p plus gamma z is equal to 0 with respect to this earlier equation. So that we can say the pressure distribution in the y direction is hydrostatic, and the term p plus gamma z is a function of x only. So, now this earlier equation number 3, which is written in the x direction, we can finally write as minus d by dx of p plus gamma z plus del tau by del y is equal to 0, equation number 5. And earlier we have seen the Newton's law of viscosity as tau is equal to mu into del u by del y. So, if you substitute for this tau here, finally we get minus d by dx of p plus gamma z plus mu into del square u by del y square is equal to 0. So, this is the final expression which we get connecting the pressure variation and the velocity variation. So, here you can see the u is only a function of y. So, that we can write del square u by del y square can be written as derivative d square u by d y square. So, therefore, finally, we can write the expression as mu into d square u by dy square is equal to d by dx of p plus gamma z, and if you put this p tilde is equal to d by dx of p plus gamma z, finally, we can write d square u by dy square is equal to p tilde by mu, where mu is the coefficient of dynamic viscosity. And now, our aim is to get an expression for velocity. So, this expression we can integrate 2 times and then write u is equal to p tilde by 2 mu y square plus c1 y plus c2. So, now we will introduce the boundary condition. So, here you can see the boundary conditions on the plate, since due to no slip condition we can write at y is equal to plus or minus y, the velocity is 0, since due to the no slip condition the velocity is 0, from which we will get this constant of integration c1 is equal to 0, and finally we will get c2 is equal to minus p tilde y square by 2 mu. So, we get c2 is equal to minus p y square by 2 mu and c1 is equal to 0. Finally, we get an expression for u, the velocity variation is equal to minus p tilde y square by 2 mu into 1 minus y by capital Y whole square, where as we have seen the distance between the plates is 2y. So, finally, we get an expression for the velocity variation, and then we can see that with respect to the velocity variation as the velocity maximum at the center. So, y is equal to 0. So, that u max is equal to minus p tilde y square by 2 mu, and then also we can find out the average velocity v bar is equal to 1 by 2y. We can integrate between minus y2 plus y u dy, that will give the average velocity as minus 2 by 3 p tilde y square by 2 mu, or that is equal to 2 by 3 u max. And then if you introduce the term g and p bar, which we have already seen, with respect to that the final expression for velocity can be obtained as u is equal to minus y square by 2 mu d by d p plus gamma z by dx into 1 minus y by capital Y whole square, or u max also can be written as y square by 2 mu d p plus gamma z by dx, and the average velocity will be, we can show that it will be 2/3 of the maximum velocity, that is equal to minus y square by 3 mu into d of p plus gamma z by dx. So, like this we can derive the relationship for velocity, and from the velocity we can go for the other parameters like shear stress variation or pressure distribution. So, now further we will be discussing on this laminar flow the next lecture.